In the book of Genesis, creation unfolds in a clear sequence. Light first, then the heavens, then the earth, and only afterward does life appear. A world is prepared before its inhabitants arrive. Existence follows order. In Buddhist cosmology, the story is different, yet strangely aligned. Universes arise and dissolve in endless cycles. Worlds form, life appears, disappears, and forms again not once, but countless times across inconceivable ages. There is no single beginning. Only repetition, impermanence, and renewal. For most of human history, these were philosophical and spiritual ideas. Today, modern astronomy has begun to echo them in an unexpected way. What if planets, the universe's first homes, formed earlier than we ever imagined, before galaxies had fully taken shape? What if, scattered among the first generations of stars, there existed ancient worlds where water condensed, chemistry stabilized, and matter briefly crossed the threshold into life? And if so, how long would life need to appear once such a home existed? This story follows two clocks running side by side. One tracks how quickly the universe learned to build worlds. The other asks how quickly lifeless matter can become alive. On Earth, life emerged almost as soon as conditions allowed. If that pattern holds, then the deepest mystery may not be whether life existed before galaxies, but how many ancient beginnings arose, vanished, and left no trace behind. To follow that trail, we first have to decide what we are actually counting. The places that could host life, or the fragile little systems that might briefly call those places home. When we talk about a cosmic house here, we are not only thinking of a planet that looks like Earth. A house is any world where matter can settle down into something stable enough for chemistry to keep records of itself. Solid surfaces that do not melt away. Liquids that can stick around instead of boiling off. An environment where energy flows, but not so violently that everything is torn apart. That house might be a rocky planet close to a star, an icy moon kept warm by internal tides, or something stranger that we would not immediately recognize as familiar. The forces that build these houses are simple compared to what comes later. Gravity gathers clouds of gas and dust into stars and disks. Within the disk, grains of rock and ice collide, cling together, grow, and eventually become worlds. This process does not need intention, purpose, or design. It is just the long patience of physics. Given enough raw material and time, houses appear whether anyone will ever live inside them or not. A resident is something different. In this story, a resident is not a civilization, or even a plant or an animal. It is any system of chemistry that can store information about itself, make use of energy, and make copies with small variations. That is the essence of Darwinian evolution. A pattern that persists by being able to reproduce, with occasional differences that can be tested by the environment over time. When those differences affect survival or reproduction, the pattern changes from one generation to the next. The word information here does not mean words on a screen or symbols on a page. It means the exact arrangement of atoms in molecules such as DNA or RNA, or whatever plays that role in an unfamiliar biochemistry. The sequence of those molecules is a kind of memory. It remembers how to build the next copy of the resident. Change the sequence, and the instructions change. In that sense, every living cell is both a tiny factory and a tiny library, constantly reading and rewriting itself. So the first important separation is this. Houses are built by gravity and the large-scale behavior of matter, while residents arise from chemistry and the slow logic of selection. One is about assembling a place. The other is about a pattern learning how to persist. The timescales for those two processes do not have to match. A universe might learn how to build houses quickly, while taking much longer to see residents appear, or the opposite might be true. On Earth, those two clocks ticked almost on top of each other. The best current estimates place the formation of our planet at about 4.5 billion years ago. The earliest confident signs of life appear in rocks that are at least 3.5 billion years old, and there are hints that living chemistry may reach even further back. That means that, on this one world, life did not wait for half the age of the universe to pass before it began. It may have started as soon as the surface cooled, oceans formed, and the environment stopped being immediately lethal. From a human point of view, 1 billion years sounds unimaginably long. From a cosmological point of view, the delay between Earth forming and life appearing looks surprisingly short. That is the puzzle that quietly sits at the heart of this entire question. If houses can appear early, and if residents can move in quickly once conditions are right, then the window in which the universe could host life might open far earlier than our intuition suggests. There is another complication. Not every house is equally welcoming. A world can be a planet in the strict astronomical sense and still be a terrible place for chemistry to organize itself. Imagine a rocky sphere baked to a glowing surface, or a frozen ball where nothing ever melts. Even if such a world is technically a house, the rooms are unlivable. Habitability is not a switch that flips from off to on. It is a spectrum. Temperature, pressure, the presence of liquid water or some other solvent, the composition of the atmosphere, and the stability of the climate all matter. Astronomers sometimes talk about a habitable zone around a star. That phrase sounds more precise than it is. It usually means the distance at which a planet with the right kind of atmosphere could keep liquid water on its surface for a long time. It is a helpful idea, but a blunt one. Real habitability is messier. A planet a little outside that zone might hide an ocean beneath ice, heated from below by radioactive decay or tidal flexing. A planet inside the zone might lose its water to a runaway greenhouse. The label on the orbit does not decide whether residents can ever appear. Even when a house crosses the threshold into being genuinely habitable, that does not guarantee that residents will arrive. Chemistry has to discover, through blind trial and error, a way to build molecules that can copy themselves and keep their pattern going. This is what people mean when they speak about abiogenesis, the origin of life from non-living matter. It is not one single spark or event. It is a long, branching chain of reactions in which some combinations of molecules last a little longer or make more copies than others. Here we run into a hard limit on knowledge. We have only one example of abiogenesis to study, and we have lost almost all direct physical traces of it. The earliest cells have long since vanished, recycled by geology and time. What we can see are chemical signatures, fossils, and the shared features of modern life. From that, we try to reconstruct how difficult the leap from house to resident really was. Was it almost inevitable once the right conditions were present, or was it a freak outcome of a very long series of unlikely steps? With a single data point, any statistical argument is weak. Yet the timing on Earth does tell us something. It rules out the idea that life must always take most of a universe's lifespan to appear. It shows that, at least once, residents arrived relatively early in the history of their house. That is enough to keep the door open. If early planets were there, and if some of them cooled, kept their atmospheres, and held on to liquid water, then there is no obvious physical law that forbids chemistry from crossing the line into biology on those worlds as well. There is one more subtle distinction. Emergence is not the same as survival. A house can briefly become habitable, host the first fragile residents, and then lose that habitability again. A star can flare. A nearby explosion can strip away an atmosphere. The climate can swing into a frozen state. In that sense, some houses might only be open for a short season, cosmically speaking. Residents may appear, struggle for a while, and then vanish without leaving any sign that we could detect from far away. So the question we are quietly asking is not simply when could life appear, but when could stable, long-lived houses exist, in which life not only appears, but has time to change and leave traces. To even start answering that, we have to watch both clocks at once. The first clock measures how quickly the universe learned to build houses, stars, disks, planets, moons. The second measures how quickly chemistry, once given a stable environment, learns to copy itself and evolve. On Earth, those two clocks happened to overlap in a way that allowed a continuous story from molten rock to oceans to microbes to viewers watching this video. That alignment may be rare or common, we do not yet know. What we can say is that nothing in physics demands that the same alignment must wait for galaxies to grow majestic spiral arms or massive halos. To see how early houses could possibly have appeared, we have to wind the universe back to a time before there were any solids at all, and watch the raw ingredients for those first homes being forged. Those raw ingredients were once missing. There was a time when the universe could not build even a single grain of dust, let alone a world that could hold an ocean. The newborn universe began as something almost offensively simple. No stars, no planets, no solids. Just a hot, expanding fog of the lightest elements, stretched across space so evenly that, from far enough away, one region looked almost exactly like any other. In that early state, the universe was more like a fluid of pure energy and particles than a place with locations and landscapes. When cosmologists talk about the Big Bang, they are not imagining an explosion from a single point into empty space. They are describing an initial state in which space itself was dense, hot, and compressed, and then began to expand everywhere at once. In that first fraction of a second, conditions were so extreme that even familiar particles like protons and neutrons were still in the process of settling into existence. Only after the universe cooled a little could stable matter form out of that energy. As expansion continued, the temperature fell. Over time, the universe became a mix of mostly hydrogen and helium with a trace amount of lithium. Those are the lightest elements in the periodic table. Hydrogen is just a single proton with, usually, one electron. Helium is a little heavier, with 2 protons and 2 neutrons bound together. Lithium adds 1 more proton and a few more neutrons. Everything we associate with solid worlds, carbon, oxygen, silicon, iron, did not exist yet. They had not been forged. For a long while, even those light atoms could not behave in ways we would recognize. The universe was filled with radiation so intense that it kept stripping electrons away from atoms as soon as they tried to form. That created what physicists call a plasma, a state of matter where nuclei and electrons move through each other like a charged fog rather than being paired up into neutral atoms. In a plasma, light particles, called photons, keep bouncing off charged particles instead of moving freely. The universe was not transparent. It glowed, but no light could travel far without being scattered. In a world like that, there is no such thing as a stable surface. No dust grain can survive. There is nothing cooler than the background to radiate heat away into. Even if gravity could try to pull material together, the pressure from the hot radiation would push back. The idea of a house, a place where matter can sit quietly and let chemistry keep records, has no meaning in this environment. There are no tables to put anything on, not even a floor. Only after hundreds of thousands of years of expansion did the universe cool enough for electrons to attach themselves to nuclei and stay there. Cosmologists call this moment recombination, even though, in a literal sense, it was the first combination. When atoms became neutral, photons no longer scattered as often. Light began to travel long distances without being constantly deflected. The universe transitioned from opaque to transparent. The afterglow of that era still surrounds us today as the cosmic microwave background, a faint bath of light stretched into long wavelengths by billions of years of expansion. Even then, there were still no houses. What existed was a nearly uniform sea of hydrogen and helium gas, with tiny irregularities in density. Some regions were very slightly denser than others. These small differences are crucial. Without them, gravity would have had nothing to work with. Everything would have stayed spread out forever. And there would be no stars, no galaxies, no planets, and no viewers asking these questions. Gravity is a simple rule with slow consequences. Where the gas was a little denser, gravity pulled a little harder. That extra pull attracted more matter, which made gravity even stronger in that region. And so on. Over extremely long timescales, this turns small ripples into large structures. Dark matter, an invisible form of matter that interacts mainly through gravity, played a key role here. It began clumping earlier and more easily than ordinary matter, forming a kind of invisible skeleton. Ordinary gas then fell into the gravitational wells carved out by that dark matter. To a human mind, used to thinking in years and lifetimes, the phrase "over extremely long timescales" is vague. In cosmic terms, it means that it took hundreds of millions of years for these gentle ripples to grow into the first dense clouds capable of forming stars. During that interval, space itself was expanding. The background radiation was fading, and the overall temperature was dropping. This period is sometimes called the Cosmic Dark Ages. There were no stars to shine, no galaxies to light up the sky, and no planets to reflect anything. Just gas, structure forming in slow motion, and darkness. If we look at this era from the perspective of our earlier metaphor, the universe has learned how to make land, but has not yet built any actual houses. There are regions where material is starting to gather. The blueprints are being sketched by gravity, but there are no walls, no floors, nothing that chemistry can call home. The raw materials themselves are inadequate. Hydrogen and helium form stars, not rocks. They can make clouds and plasmas and glowing nebulae, but they cannot, by themselves, make continents or ocean basins or mineral surfaces for complex molecules to cling to. The reason is deeply tied to the structure of atoms. Heavy elements, like carbon and oxygen, have more protons in their nuclei and more electrons in their outer shells. That extra complexity allows them to form a wide variety of chemical bonds. Carbon, for example, can link itself into chains, rings, and three-dimensional frameworks. That flexibility is why it is the backbone of organic chemistry. Oxygen, combined with hydrogen, makes water, a liquid that can dissolve many substances and support rich chemistry. Silicon and iron form strong solids and dense cores. None of that was present yet. So the newborn universe faced a kind of paradox. It contained almost all the energy and matter that would ever exist, but very little structure. It had the ingredients to make light elements, but not to make the heavy ones needed for solid surfaces and complex molecules. It could grow clouds, but not worlds. For houses to appear, something had to happen that could forge new elements out of the old ones. That something would be the first generation of stars. From the standpoint of our two clocks, we can say this: the resident clock has not even been wound yet. Without heavy elements, there is no obvious way to form the diversity of molecules needed for life as we understand it. The house clock is only just starting. Gravity is gathering gas into denser knots, but no stars have ignited, no planets are orbiting anything, and no moons are circling them. The universe is pregnant with structure, but still almost featureless. It is tempting to imagine that, because the early universe was dense and energetic, it might have somehow hosted exotic forms of life based on physics unfamiliar to us. There are speculative ideas about life in very different conditions. But in this story, we are choosing a conservative path. We are asking a narrower question. When did the universe first become capable of supporting life based on chemistry? On atoms forming molecules? On reactions that can store and copy information? That requires heavy elements, cooler environments, and stable surfaces or liquids. The newborn universe offered none of those. What it did offer was time and a set of simple rules: expansion, cooling, gravity, quantum mechanics, shaping how matter clumps and radiates. These rules, playing out over hundreds of millions of years, would eventually create the first true engines of transformation. Stars massive enough and hot enough in their cores to fuse light elements into heavy ones. Only when those stars were born, lived, and died would the periodic table expand beyond its initial, stripped-down state. From our perspective now, with planets under our feet and metals in our hands, it is easy to assume that such richness is the default state of matter. It is not. For a significant fraction of the universe's early history, nothing we would recognize as a home could exist anywhere. No planet, no moon, no asteroid, no icy shell hiding an ocean. Just a young cosmos waiting for its first generation of fire to begin the long, slow work of turning simple ingredients into the building blocks of houses. Only then could the other clock, the one tracking the possibility of residence, begin to move at all. The first tick of that second clock was not a quiet one. It arrived as points of fierce, concentrated light, burning into the darkness that had waited so long to be disturbed. Those first stars did not form everywhere at once. They were born in pockets where gravity had been allowed to work undisturbed during the long, dark interval after the universe became transparent. In those slightly denser clumps of gas, ordinary matter followed the invisible scaffolding laid down by dark matter, falling inward until its own weight squeezed it into something new. Where the collapse was strongest, pressure and temperature climbed high enough for nuclear reactions to begin. Hydrogen in the center of those clouds fused into helium, and the first stars ignited. To human eyes, if human eyes had existed, these stars would have looked nothing like the gentle, yellow sun that now warms Earth. Many of them were enormous by our standards, with masses tens or even hundreds of times larger than the Sunday. Some models even suggest that a few might have reached masses of several hundred solar masses, swollen and short-lived. Their surfaces blazed at temperatures far hotter than the sun's. They poured out ultraviolet light, the high-energy radiation that is powerful enough to tear electrons away from atoms. Ultraviolet is a word that simply means beyond violet. It refers to light with wavelengths shorter than what our eyes can see. This kind of light carries more energy per photon, which makes it especially effective at ionizing gas. The newborn universe was full of neutral hydrogen, atoms in which protons and electrons had finally settled together. When ultraviolet light from the first stars washed over that gas, it stripped those electrons away again, turning the surroundings back into a thin, ionized plasma. This is what cosmologists call reionization. It was not an instantaneous transformation, but a gradual clearing of a cosmic fog. Around each first star, or small group of stars, there would have been a growing bubble of ionized hydrogen, a region where the gas had been turned into a transparent, hot plasma. As more stars formed, these bubbles expanded and began to overlap. Over hundreds of millions of years, more and more of the universe shifted from neutral to ionized. The darkness of the cosmic night thinned into a pale, glowing mist. The phrase cosmic dawn refers to this broad era when the first stars and galaxies turned on. It is not a single moment, but a stretch of time beginning perhaps a couple of 100 million years after the Big Bang and extending through the first billion years or so. During this interval, the first stars lit up, the first small galaxies assembled, and the neutral hydrogen between them was gradually cleared. Recent observations from the James Webb Space Telescope have found galaxies whose light left them only a few 100 million years after the Big Bang, already showing signs that they were carving ionized bubbles around themselves. That tells us that cosmic dawn may have begun earlier and with more intensity than older theories expected. The first generation of stars, often called the primordial population, were made from gas that contained almost no elements heavier than helium. Astronomers refer to those heavier elements, carbon, oxygen, silicon, iron, and so on, as metals, even though many of them would not be metals in the everyday sense. This is a specialized usage. In astrophysics, metallicity means the fraction of a star's mass that is in elements heavier than helium. The first stars had extremely low metallicity. They were built from almost pristine primordial gas. Inside their cores, that would not remain true for long. Nuclear fusion in stars acts like an element factory. In the intense heat and pressure of the central regions, hydrogen fuses into helium. In more massive stars, helium can further fuse into carbon and oxygen. Still, heavier elements can be produced in later stages of stellar evolution or in the extreme violence of stellar deaths. The first massive stars therefore served as the universe's initial forges. taking the simple output of the Big Bang and turning it into the richer periodic table needed for planets and life. These stars did not live long. The more massive a star is, the faster it burns its fuel. While a star like the Sun can shine for around 10 billion years, a star tens of times more massive might live only a few million years before collapsing or exploding. The most massive might burn themselves out in a fraction of that time. From a cosmic perspective, they were brief flashes. Yet, in those short lives, and in their deaths, they transformed their surroundings. When such a massive star reaches the end of its life, it can become unstable. Its core may collapse, triggering a supernova, a titanic explosion that blows the outer layers of the star into space at high speed. In that moment, shock waves and extreme conditions create many of the heavier elements, including some needed for complex chemistry. Those elements are then mixed into the surrounding gas. Over time, that enriched gas can cool, fragment, and form new stars, and, eventually, solid grains of dust. In this way, cosmic dawn was both an awakening and a kind of violence. The first stars carved hot, ionized cavities in the gas around them and flooded space with harsh radiation. They also seeded that space with the very elements that would later allow dust, rocks, oceans, and potentially residents to exist. Every future metal-rich world would trace its ancestry back through many generations of stars. But the lineage begins here, with these early giants. As more stars formed, they tended to gather into gravitationally bound systems. What we now call galaxies grew out of the same dark matter skeleton that had shaped the first overdense regions. At first, these galaxies were small and irregular, collections of gas and stars held together more by their shared gravity than by any grand structure. They were far less massive and far less organized than a modern spiral galaxy like the Milky Way. Yet, even these early assemblies mattered. They provided deeper potential wells where gas could cool and condense repeatedly, fueling cycles of star birth and star death that enriched their surroundings further. When astronomers observe these early galaxies today, they do so by catching light that has been stretched by cosmic expansion. The concept used to describe this stretching is called redshift. As the universe expands, the wavelength of light traveling through it is stretched, moving toward the redder, lower energy part of the spectrum. The higher the redshift, the earlier the light was emitted. By measuring how much a galaxy's light has been shifted, astronomers can estimate how long that light has been traveling, and thus how far back in time they are looking. Some of the galaxies now detected at very high redshifts show features that suggest they are already influencing their environments in dramatic ways. For instance, when we see strong emission in specific spectral lines associated with ionized hydrogen, it implies that those galaxies have carved out large ionized regions around themselves. That, in turn, implies intense ultraviolet output from either massive stars, active black holes, or both. In other words, even relatively small early galaxies can act as powerful beacons, reshaping the medium around them. From the point of view of houses and residents, cosmic dawn is the universe's first serious attempt at preparing building materials. Before these stars, the cosmos had almost no way to create solid surfaces or complex molecules. After them, the gas between stars was no longer chemically simple. It contained trace amounts of carbon, oxygen, nitrogen, silicon, and iron. Grains of dust could condense out of cooling gas, providing the seeds around which future planets and smaller bodies would grow. At the same time, this was a perilous era for any potential chemistry that tried to organize itself. Ultraviolet radiation from the first stars, and from the galaxies they helped form, was capable of breaking apart molecules and stripping atmospheres from small worlds. Supernova explosions sent shockwaves through nearby gas clouds, compressing them in some places and dispersing them in others. The same events that enriched space with heavy elements could also sterilize large regions repeatedly. This is the contradiction that sits quietly in the heart of cosmic dawn. The universe became capable of making houses only by unleashing forces that would be dangerous, even lethal, to residents. To us, looking back now, it is clear that both aspects were necessary. Without heavy elements, there would be no rocky planets, no complex chemistry, no stable solvents like liquid water. Without intense radiation and shocks, gas clouds might never have fragmented in ways that favored the formation of diverse structures. But any hypothetical early resident would have experienced this as a profoundly unstable neighborhood. Yet, on the longest timescales, the direction of change is unmistakable. From a nearly homogeneous fog of hydrogen and helium, the universe progressed to a patchwork of bright knots and enriched gas, threaded across vast distances. The first stars marked the initiation of a feedback loop. Stars create heavy elements and radiation, which change how future stars form, which in turn change the environment again. Every subsequent generation of matter inherits the chemical and structural history of those that came before. By the end of cosmic dawn, the universe was no longer a place where houses were impossible in principle. It had pockets of gas with enough heavy elements to form dust. It had regions where gravity had gathered matter into disks around young stars, where grains could begin to stick together. It also had plenty of hazards. But for the first time, the basic requirements for habitable homes were starting to be assembled in scattered, fragile attempts. The two clocks we are following are no longer frozen. The house clock is ticking faster as galaxies grow and successive generations of stars enrich their surroundings. The resident clock, however, is still largely silent. Chemistry has more tools to work with now, but in most places, there are still no solid surfaces, no stable oceans, no long-lasting niches where complexity can accumulate. The question that hangs over this era is simple and hard to answer. In some corner of this early restless universe, could a house have become calm enough, rich enough, and persistent enough for the other clock to start as well? The first places calm enough to matter did not arrive as finished worlds. They began as dust drifting in the light of new stars, as if the universe were practicing the idea of a planet before committing to one. When a cloud of gas collapses to form a star, it almost never collapses perfectly straight in. Any small bit of spin is amplified as the cloud shrinks. Like a skater pulling in their arms and spinning faster, the tightening cloud turns into a flattened, rotating structure. Astronomers call this a protoplanetary disk. A broad, thin disk of gas and dust swirling around a young star, where proto just means in the process of becoming. This disk is the workshop where houses are built. Most of the disk is hydrogen and helium, light gases that will never become solid on their own. The interesting part, for our story, is the tiny fraction made of heavier elements, grains of silicates, bits of carbon, droplets of frozen water, and other ices. They are small, often microscopic, but they have something the gas does not. They can collide and stick. At the scale of dust, a gentle collision does not shatter. Electrostatic forces help grains cling together. These first unions are fragile, but they are the beginning. In the early stages, the process is quiet and almost invisible. Particles settle toward the midplane of the disk, where the gas is densest. As they jostle and collide, they grow from dust grains to pebbles, from pebbles to rocks. This phase is sometimes called coagulation, a word we also use for blood clotting, because it captures the same idea. Small pieces joining into something larger and more coherent. Nothing here yet resembles a world. It is still just debris, but the debris is thickening. Once these clumps reach sizes measured in many meters, another force begins to matter. Gravity. Not just from the star, but from the clumps themselves. Any solid body has gravity, no matter how small. When enough mass is gathered into one place, its pull on nearby material becomes noticeable. It starts to attract other rocks, sweeping up fragments and growing faster. Astronomers call these growing bodies planetesimals, literally almost planets. They might be tens of kilometers across or larger, rubble piles held together by their own weight. Here, the building process changes character. Before, growth was slow and gentle. Now, it can become runaway. A slightly larger planetesimal has slightly stronger gravity, so it collides with and captures more material, becoming larger still. That extra advantage compounds. Over time, a few bodies in the disk can outgrow their neighbors, turning into planetary embryos, incomplete worlds, still sharing orbits and still in danger of dramatic collisions. The timescale for this transformation from dust to embryos is short in cosmic terms. In many models, the inner parts of a disk can assemble planetary cores in something like a few million years. That is a small fraction of the lifespan of a typical star. It means that once the raw ingredients are there and a disk has formed, houses can be built quickly compared to the age of their neighborhood. The universe does not need to wait for galaxies to grow grand structures before it can try building planets. It only needs a star, a disk, and a sprinkling of heavier elements. We know this not only from theory, but from watching disks around young stars today. Telescopes like the Atacama Large Millimeter Array, a collection of radio dishes in the Chilean desert, can image protoplanetary disks in detail. In many of those images, we see rings, gaps, and spiral patterns carved into the dust. Those structures are best explained by the presence of forming planets already tugging on the material around them. In other words, by the time a star is still very young, the disk is already being sculpted by unseen houses in progress. A protoplanetary disk is not uniform. Closer to the star, temperatures are high. Ices evaporate, and only the most refractory materials, silicates and metals, can remain solid. Farther out, beyond a certain distance, it is cold enough for water and other volatile substances to freeze. Astronomers call this boundary the snow line. Inside the snow line, building materials are mostly rock and metal. Outside it, there is much more solid material, because frozen water and other ices add to the mass. That difference shapes which kinds of planets can grow where. The snow line acts like a quiet dividing line in the housing market. Inside it, the supply of solid matter is limited. Planets there tend to be smaller and rocky, like Earth and its neighbors. Outside it, the abundance of ice means that planetary cores can grow much more massive. Once a core reaches a certain size, it can start to pull in gas directly from the disk, wrapping itself in a thick atmosphere of hydrogen and helium. That is how gas giants are thought to form. A solid heart, born in the icy outer regions, swollen by a vast envelope of gas. This picture becomes more complicated when we remember that planets do not always stay where they are born. As a planet interacts gravitationally with the gas in the disk, it can exchange angular momentum with it, migrating inward or outward. This is how we think some gas giants ended up very close to their stars, in orbits far tighter than the one Mercury has around the Sunday. These hot Jupiters, as they are nicknamed, were almost certainly not born in those blistering orbits. They migrated inward, dragging their houses into dangerous neighborhoods after they were already mostly built. Migration matters for our story because it means that the arrangement of houses in a planetary system is not fixed by their birth positions. Habitable zones, those ranges of distance where liquid water could exist on a planet's surface, can be crossed by migrating worlds. Small planets might be scattered inward or outward by larger ones, ending up in unexpected places. Some houses may be thrown entirely out of their systems, becoming lonely planets drifting between the stars with no sun at all. Others may be nudged into orbits where conditions are more gentle than where they were born. What matters for the question of early houses is not the exact architecture of these systems, but how easy the basic process appears to be. Dust to pebbles to rocks to planetesimals to planets. Each step has uncertainties, but none of them seem to require conditions unique to the modern universe. They rely on gravity, collisions, cooling, and the presence of at least some heavier elements. That means that as soon as the first generations of stars had seeded space with those elements and formed disks, the machinery to build planets was in place. In regions where the chemical metallicity was low, that is, where the fraction of heavy elements in the gas was much smaller than in our local neighborhood, the process would be less efficient. There would simply be fewer solid grains per unit of gas. but models suggest that even a tiny fraction of heavy elements, far less than what we see around the Sun today, is enough to allow dust grains to form and grow. The difference is not between possible and impossible, but between common and rare, or between fast and slow. Observations support that interpretation. Astronomers have found planets orbiting stars that are themselves quite poor in metals, stars that formed when the universe was younger and less chemically enriched. These planets may not look like Earth, some may be dense, scorched worlds hugging close to their stars. Others may be lighter, with thick gaseous envelopes. But their very existence tells us that nature does not need a perfectly stocked chemical pantry to attempt building houses. It will work with whatever is available. Inside a forming planetary system, the diversity of houses can be astonishing. Small rocky worlds near the star, larger icy bodies farther out, moons forming around massive planets, themselves potential homes with internal oceans kept liquid by tidal flexing. Asteroid belts that never quite manage to assemble a single dominant planet. Comets storing frozen volatiles in reservoirs at the edges of the system, occasionally diving inward to deliver water and organic molecules to inner worlds. All of this structure emerges from the simple starting point of a star surrounded by a flattened disk of gas and dust. Each of these potential houses comes with its own balance of risk and stability. A moon with a subsurface ocean might be protected from stellar radiation by an ice shell, yet dependent on the tidal pull of its planet to keep its interior warm. A rocky planet in a stable orbit within the habitable zone might still be subject to giant impacts during the last chaotic stages of formation, repeatedly sterilizing its surface. A small world, on an eccentric path, might experience wild swings in climate over each orbit, never quite settling into a steady state. At this stage in cosmic history, though, something fundamental has changed. Houses are no longer ruled out everywhere. They are being tried in millions of variations, around stars of different masses and in galaxies of different shapes. Some of these attempts will be short-lived. The host star may be massive and unstable. The surrounding region may be bathed in harsh, ultraviolet radiation from nearby giants. A passing supernova may strip atmospheres or heat surfaces beyond endurance. But between those extremes, there will be quieter corners, disks feeding smaller stars in less crowded suburbs of their galaxies. In those quieter systems, the same physics that builds planets around young stars today would have been at work long ago. Dust grains settling, planetesimals coalescing, embryos colliding in slow, catastrophic mergers that release enough heat to melt whole worlds. Iron sinking to form cores, silicates floating to become mantles and crusts, volcanoes venting gases to create atmospheres, water arriving as ice from outer regions, or condensing from the disk itself. These processes do not require modern galaxies. They require only a modest enrichment in heavy elements and enough time for gravity and collisions to do their work. From the viewpoint of a resident, if any ever appeared in those ancient systems, the sky might look unfamiliar. The host galaxy could be smaller, its structure less grand. The background might hold fewer distant, heavy elements, rich stars. But the local conditions on a planetary surface, a rocky plain, an ocean under a sky, a source of energy shining from above or welling from below, could be surprisingly similar in their essentials to what we recognize. Chemistry does not care how mature a galaxy looks from the outside. It cares about temperature, pressure, and the availability of certain kinds of atoms. So, by the time galaxies were still in the process of assembling, the universe already possessed the tools to build houses. Not everywhere, not with the abundance and variety we see now, but enough to make the question meaningful. In some of those first planetary systems, the gap between dust and world was already being bridged. The slow machinery had already turned. The floors had been poured, the walls raised. The lights, in the form of young stars, were on. What remained uncertain was whether any of those early houses ever stayed calm for long enough that the second clock, the one that measures the arrival of residents, could begin to tick as well. Some of those early houses may have started smaller than we usually imagine, more like half-built shelters on a construction site than finished homes, yet still with corners where chemistry could have tried to settle. In a young planetary system, not every clump of rock and ice makes it all the way to becoming a planet. The disk around a newborn star spawns a whole population of leftovers, fragments, lumps, and half-grown bodies that never gained enough mass to dominate their orbits. Astronomers call many of these pieces planetesimals, a word that simply means almost planets. They are big enough for their own gravity to matter, but not big enough to reshape their neighborhoods the way a true planet does. Some planetesimals remain as solitary wanderers. Others gather into belts, vast swarms of icy and rocky objects that circle their star like a diffuse ring. In our own system, the asteroid belt between Mars and Jupiter and the icy Kuiper belt beyond Neptune are examples of such regions. The Kuiper belt is basically a reservoir of frozen debris far from the sun, where sunlight is weak and temperatures are extremely low. Worlds there are dark, cold, and slow, preserving ancient conditions, the inner planets destroyed long ago. When we look at objects in these belts today, we are peering into a kind of archive. Bodies like the contact binary Arakoth, visited by a passing spacecraft, seem only lightly processed since the earliest days of the solar system. A contact binary is an object made of two lobes that gently merged, sticking together rather than shattering. The result looks like two spheres touching, frozen at the moment of union. That shape hints at a gentle environment where collisions could build structures rather than always grinding them down. These small worlds tell us how easy it is for matter to assemble into something more complex than dust without ever becoming a planet. It does not take a thick atmosphere, or plate tectonics, or even a large mass. It only takes a population of grains with enough time to drift, collide, and cling. The first generation of metal-poor disks in the early universe would have had fewer grains, but the same physics. If full-size planets were rare at first, swarms of smaller bodies were almost certainly not. Whether these primitive bodies can count as homes depends on what we demand from a home. Most of them are too small to hold onto a thick atmosphere. Their surfaces are bombarded by radiation and cosmic rays. Temperatures can swing wildly between day and night. On many of them, ice is exposed directly to space, slowly sublimating away. At first glance, they look more like rubble than shelter. Yet the story is more interesting just beneath the surface. Even a small world can have some internal heat. Radioactive elements embedded in rock decay over time, releasing energy. If the body is in a stretched, elliptical orbit around a planet or star, changing gravitational pull can flex its interior. This process, called tidal heating, works a bit like squeezing a rubber ball in your hand. The constant deformation produces warmth. In larger moons, tidal heating can sustain subsurface oceans beneath thick ice shells. In smaller bodies, it may simply keep internal pockets of ice near their melting point. A subsurface ocean is exactly what it sounds like. A layer of liquid water trapped between a rocky core and an outer shell of ice. Because it is sealed away from space, it does not depend on gentle sunlight or a friendly surface climate. Energy comes from below, and the ice roof shields whatever lies beneath from radiation and impact damage. We know that such oceans exist in our own system today, in places like Europa and Enceladus, moons that orbit giant planets. It is not difficult to imagine similar arrangements around early giant planets, even in galaxies that were still assembling. On a smaller scale, tiny pockets of liquid can also form inside porous ice and rock. As a primitive body slowly warms or cools, regions within it can cross the boundary where ice melts or refreezes. Water moving through cracks and pores can carry dissolved minerals, setting up simple chemical gradients. A chemical gradient is just a difference in concentration between two regions, the kind of imbalance that life later learns to exploit as a source of energy. Even in a world with no stable oceans, such gradients can exist. There is another feature of primitive bodies that matters for our question. Their surfaces are rich in organic chemistry. Observations of comets, asteroids, and interstellar clouds show that simple organic molecules, including some that resemble amino acids and sugars, can form in cold, irradiated ices. These molecules are not life, but they are part of the moving-in kit for residents, the basic components from which more complex structures might eventually be built. When a comet or icy planetesimal is heated, those organics can be released, concentrated, or altered in new ways. Taken together, this suggests a layered picture of habitability. At the top, we have fully fledged planets, with atmospheres, oceans, and long-term climates. Beneath that, we have moons with subsurface oceans, protected from space but still geologically active. Beneath those, a whole spectrum of primitive bodies, some almost inert, others with fleeting pockets of liquid, chemical gradients, and rich organic surfaces. The early universe may have produced many more of these modest homes than the grander houses that attract most of our attention. The downside is that such places are fragile. A small world cools quickly. Its internal heat leaks away. Tidal heating can stop if orbits change or resonances break. Impact events can disrupt thin crusts or strip material entirely. Worse, in the crowded young environments where many of these bodies formed, gravitational encounters could easily eject them from their systems altogether. A free-floating planetesimal or moon drifting through interstellar space may retain some internal warmth for a while, but its long-term prospects as a home grow dim. Yet, if we are only asking about the possibility of life starting, rather than surviving for cosmic ages, fragility might be enough. A primitive body with liquid water pockets, abundant organics, and energy sources could, in principle, host the early stages of prebiotic chemistry. Molecules could explore combinations, form larger structures, and perhaps stumble toward crude self-copying systems. If those systems never learned to stabilize their environment, or if the environment changed too quickly, they might vanish without ever leaving signatures that could escape their tiny world. From the perspective of our two clocks, primitive bodies show us that the universe had many chances to start the resident clock in a small way before finishing its work on large planets. The house clock was already ticking at the scale of dust and planetesimals. What these rough shelters lacked in comfort, they made up for in number. Each one was a lottery ticket, a brief experiment in how far chemistry could go under harsh, constrained conditions. When we hold a meteorite in a museum, or watch a comet flare as it approaches the sun, we are touching the remnants of those experiments. They are not failures exactly. They are simply houses that never got the chance to be fully lived in. In a younger universe, under harsher skies, and within smaller galaxies, there may have been many more like them, scattered and forgotten. Whether any of them ever managed, even for a short time, to cross the threshold from chemistry to biology is a question that sits in that quiet space between what is possible and what is knowable. To see how far the universe actually pushed that possibility, we have to stop imagining and look at the oldest real houses we have found, the ones still standing after almost the entire age of the cosmos. They are faint, distant, and quietly at odds with how we once thought worlds should appear. The universe today is a little over 13.5 billion years old, according to measurements of the ancient light left over from the hot beginning. For a long time, many astronomers assumed that truly interesting planetary systems would be late developments in that story. Planets, especially small rocky ones, were expected to prefer stars rich in heavy elements, the kind that accumulate only after many generations of stellar birth and death. The early universe, thinly enriched and still chemically young, seemed like a place that should not yet know how to build intricate houses. The evidence has not been kind to that assumption. One of the clearest challenges comes from a system given the catalogue name Kepler 444. Around an orange, sun-like star in the constellation Lyra, the Kepler spacecraft found a family of 5 small planets, each roughly between Mercury and Venus in size. The age of the host star has been estimated at a little over 11 billion years, meaning that this planetary system formed when the universe itself was only a few billion years old, perhaps less than 1/5 of its current age. The houses there are ancient by any standard we can conceive. Kepler 444 is not just old, it is also relatively poor in heavy elements. In astrophysics, that poverty is described using the word metallicity. Here, Metals does not just mean substances like iron and copper. It is a technical term for all elements heavier than helium: carbon, oxygen, silicon, iron, and the rest. A metal-poor star is one that formed from gas which had seen only a small amount of previous stellar processing. For such a star to host multiple small rocky planets means that even a sparse sprinkling of heavy atoms was enough to build solid surfaces very early. The orbits of these ancient planets hug their star tightly. Each one circles in far less time than Earth takes to go around the Sun, completing a year in less than the span of a couple of terrestrial weeks. They are probably too hot on their surfaces for any kind of familiar habitability. Yet, that is not the point. Their existence is the important part. They show that the universe was assembling compact, rocky houses when galaxies were still in their youth. The house clock had begun to tick fast, long before ours did. Another old address sits in a different neighborhood of the Milky Way. In what astronomers call the thick disk, the disk of our galaxy is not a single, flat, uniform structure. It has components. A thin disk, where many younger, metal-rich stars live, and a thicker, puffier disk, populated by older, more metal-poor stars with orbits that take them higher above and below the galactic plane. The star catalogued as TOI 561 lives in that thicker, older component. It is an orange dwarf, somewhat smaller and cooler than the Sun, with an estimated age of around 10.5 billion years. Around this star, astronomers have found several planets, including an ultra-short period super-Earth that races around its star in less than a terrestrial day. A super-Earth is a planet larger and more massive than Earth, but smaller than the gas giants, often imagined as rocky or partially rocky worlds with thick atmospheres. An ultra-short period planet is one so close to its star that its year is measured in hours rather than days. These worlds are expected to be extremely hot, often molten at the surface. Observations with the James Webb Space Telescope have provided evidence that this inner planet still carries a substantial atmosphere, despite orbiting an ancient, iron-poor star at a distance so close that its surface is likely a global magma ocean. The atmosphere appears to be dense and volatile, rich, perhaps cycling gases between the molten surface and the air above like a kind of slow breathing. Whatever the details, the lesson is unsettlingly simple. Even in a harsh, old environment with relatively few metals, planets can form, persist, and carry complex structures like atmospheres for billions of years. If we step further out, beyond the main disk of the galaxy, we encounter yet older houses in even stranger settings. One of the most evocative examples orbits in the globular cluster Messier 4, a dense, spherical swarm of stars that formed in the very early history of the Milky Way. Globular clusters are gravitationally bound collections of hundreds of thousands of stars, packed into a relatively small volume and thought to be among the oldest stellar populations in a galaxy. In this particular cluster, astronomers discovered a planet orbiting a pair of exotic remnants, a pulsar and a white dwarf. The pulsar is a neutron star, the collapsed core of a massive star that ended its life in a supernova, spinning rapidly and emitting beams of radio waves like a lighthouse. The white dwarf is the compact, cooling core of a less massive star that has shed its outer layers. Around this unlikely pair, a planet moves in a wide orbit. Because the age of the entire globular cluster can be estimated from the properties of its stars, the planet inherits that age. The cluster appears to be about 12 and a bit billion years old, making the planet likely nearly that old as well. It is often nicknamed the Methuselah planet, after the long-lived figure in ancient scripture. This is not a gentle suburban home. The planet orbits in a crowded stellar city, where the gravitational pulls of passing stars can rearrange orbits, and where at least one supernova has already happened, leaving behind the pulsar. Yet the world persists. It may have formed early, alongside its original host star, then survived a supernova and a three-body dance that left it bound to a new pair of stellar remnants. Or it may have been captured later. Either way, it tells us that planetary bodies can endure in environments and histories very different from our own. Each of these systems, the compact rocky worlds of Kepler 444, The blistering super-Earths of TOI 561, the ancient giant in Messier 4, pushes against a narrative in which planets are late, fragile luxuries. They show that once the universe had even a modest inventory of heavy elements, it began building houses almost everywhere it could. Not perfect houses, not always comfortable, not always long-lived, but recognizably planets, orbiting recognizable stars. At times when our own galaxy was still young. There is another layer to this story. When astronomers study the statistics of exoplanets, they see a trend. Stars richer in metals are more likely to host giant planets. This is sometimes called the planet metallicity correlation. It makes intuitive sense. With more heavy elements in the disk, there is more solid material to build the cores that eventually grow into gas giants. For a while, it was tempting to extend that intuition to all planets and all times, to imagine the early, metal-poor universe as a place where planet formation would be severely suppressed. The ancient systems we have just walked through complicate that picture. They do not erase the trend. High metallicity still seems to favor the formation of certain kinds of planets, but they show that the threshold for building worlds is lower than we might have thought. The universe does not need a pantry full of heavy elements to attempt making houses. A thin scattering will do, especially for small, rocky planets. When we find such planets orbiting stars that formed when the universe was young, we are looking at the successful outcomes of those early, frugal experiments. Of course, the existence of a house does not tell us anything directly about residents. Kepler 444's planets may have spent their whole lives as airless, scorched stones. The super-Earth by TOI 561 may always have been an inferno wrapped in thick, toxic gases. The Methuselah planet, if it carries any atmosphere at all, may be a frozen giant under dim, flickering radiation from a pulsar and a cooling white dwarf. Yet the fact that such places exist, and have existed for most of cosmic history, opens a space in our thinking. We can no longer honestly say that the universe waited patiently for galaxies to mature before learning to build planetary homes. It did not. The oldest houses we know are nearly as old as the oldest stars we can date. Some formed when the cosmos itself was only a small fraction of its current age. Some have endured through supernovae, cluster dynamics, and the changing chemical makeup of their surroundings. They are not comfortable, but they are real. From the perspective of our two clocks, these discoveries tighten the constraints. The house clock began ticking early and has been busy ever since, even in metal-poor environments. The resident clock remains largely hidden from us, but we now know that it did not have to wait for the richest conditions imaginable. In principle, there were solid surfaces, atmospheres, energy sources, and long spans of time available in the universe long before Earth formed. Whether anything ever moved into those houses is a different question. The oldest homes we see simply remind us that the door was open far earlier than the familiar story suggests. Someone has to cross that doorway for a house to become more than architecture. The trouble is, the moment we try to name that someone, our imagination sprints far ahead of what the universe actually gives us. In everyday language, the word life carries a lot of baggage. We picture animals, forests, cities, conversations. We imagine intentions, feelings, stories. None of that can help us much at the scale we are dealing with here. In the early universe, if any residents existed at all, they were not storytellers. They were chemistry that had learned a single strange trick, how to keep its own pattern going. So, to talk honestly, we need a quieter word than life. We will keep using the word resident, but now we have to say what that means. Not as a fantasy, not as a wish, as a set of physical behaviors that matter for this question. A resident, in the sense we need here, does three things. First, it stores information about itself. There is some structure that lasts long enough to matter. A sequence of molecules, a pattern in a membrane, a specific arrangement that can be copied. This is what makes DNA and RNA so central to life on Earth. They are not special because of their letters. They are special because they can hold a detailed description of how to build the next copy. Second, it uses its environment. That means taking in energy and matter and pushing them through a controlled series of reactions. This is what biologists call metabolism. At its simplest, metabolism is just a network of chemical reactions that works together as a whole, not as scattered, isolated events. Instead of every molecule acting alone, a resident channels reactions into cycles, pathways, and feedback loops. Third, it makes copies with variation. It reproduces, and those copies are not perfect. There are mistakes, changes, or noise in the copying process. Over time, those small differences are tested by the environment. Some copies last longer or make more copies. Others vanish. That process is Darwinian evolution. There is no intention behind it. It is simply what happens whenever you have replicators, variation, and competition for limited resources. If a system does all three of these things, even clumsily, it is a resident by the standard we are using. It may be fragile, it may be simple. It may never build a civilization or a forest, but it has stepped across a line that ordinary chemistry never crosses. This definition is deliberately narrow. It does not require intelligence. It does not require movement or senses or a nervous system. A bacterial cell drifting in the ocean qualifies. A strand of RNA in a simple compartment, copying itself with occasional mistakes and stealing energy from its surroundings, would qualify. A complex mixture of molecules that reacts in interesting ways but never stabilizes into a self-copying pattern does not. There is a reason for this caution. The universe is full of patterns that look alive if we squint. Flames grow, spread, and consume fuel. Crystals grow in regular shapes that seem almost purposeful. Storm systems form, persist, and die. But none of these store a detailed internal description of themselves that can be copied and varied. A crystal does not remember a recipe. It simply adds more of the same units to its structure wherever it can. When astrobiologists think about life, this is the kind of distinction they are trying to hold. The discipline of astrobiology is the study of life in its broadest possible context, how it begins, how it might exist elsewhere, what its limits are. But because we have only Earth as a confirmed example, the field has to work with definitions rather than a catalogue. It asks, essentially, what minimum behaviors must a system show before we are willing to say that it is more than chemistry, that it is a resident? Even on Earth, the boundary is blurry. Viruses replicate, but only inside host cells. They carry genetic information, but they do not have their own machinery for metabolism. They borrow it. Some scientists argue that viruses are not truly alive. Others say they are part of the living world, just deeply parasitic. Prions, infectious proteins that cause diseases by making other proteins misfold, sit even closer to the edge. They are patterns that spread, but they do not carry genetic code in the usual sense. At the opposite extreme, there are purely chemical systems in the laboratory that imitate some behaviors of life. Researchers have built autocatalytic sets, collections of molecules, in which each reaction produces products that help drive other reactions in the same network. The term autocatalytic simply means that the system helps to catalyze or speed up its own reactions. These networks can persist and even adapt in simple ways, but they do not yet meet all three criteria. They hint at how residents might emerge, but they are not residents themselves. Between these examples lies a twilight zone of possibilities. Protocells, pre-cellular systems, strange hybrids we have not yet created or discovered. A protocell, in this context, means a simple compartment, perhaps a droplet of fat, like molecules called lipids, containing some kind of replicating chemistry. The compartment can grow and divide. The molecules inside can change. Information, metabolism, and reproduction begin to entangle. At some point along that spectrum, the label resident becomes more justified than interesting chemical droplet. There is no sharp line. For our cosmic question, that ambiguity matters. If we defined residents only as complex cells with DNA, proteins, and sophisticated metabolisms, we would be demanding a lot from the universe before allowing that residents existed. If we instead allowed any self-sustaining pattern at all to count, we would erase the difference between life and many non-living systems. The compromise we have chosen is this functional definition. It is strict enough to exclude most simple physics, and broad enough to include unknown biochemistries. Notice something quiet but important here. The definition says nothing about the particular atoms used. On Earth, carbon plays the central role in building complex molecules, and water is the primary solvent. That may not be the only way to do it, but it is a well-tested one. From a physical point of view, the key properties are flexibility in bonding and the ability to form stable, complex structures. Carbon excels at that. Other elements, like silicon, have been suggested, but so far we have no clear examples of silicon-based residence anywhere. Similarly, the solvent does not have to be water in principle. A solvent is a liquid that can dissolve other substances, allowing molecules to move, meet, and react. Water has a very wide temperature range in which it is liquid, and its structure makes it good at mediating many types of chemical interactions. In the cold outer regions of some planetary systems, other liquids, such as liquid methane or ethane, may take on a similar role. On the surface of a moon like Titan, rivers and lakes of such hydrocarbons flow under a thick atmosphere. Some researchers have speculated about the possibility of exotic residence in such environments, but so far it remains speculation. What matters for our definition is not the specific choice of atoms or solvent, but the pattern of behavior. Information, storage, metabolism, and Darwinian evolution. If some alien chemistry in a distant, early planetary system managed to build residence using a solvent, we would find strange and elements in unusual ratios. They would still fit. If they never managed those three behaviors, even if their molecules were elaborate and their environment complex, they would not. There is another quiet constraint hiding underneath all this. For Darwinian evolution to work, there must be a way for information to change gradually. A system that jumps from one completely unrelated configuration to another cannot accumulate small improvements. That is why genetic code is built on small units, like letters in an alphabet, that can be swapped, duplicated, or deleted. It is why metabolism uses networks of reactions that can be extended, rerouted, or fine-tuned. The structure of a resident must be such that tiny changes can matter. This matters when we think about early cosmic residence because it limits what kinds of instant life scenarios make sense. The universe is not likely to assemble a highly complex resident in a single accident, the way a story might conjure a sudden, fully formed organism. It is more plausible that simple replicators appeared first, with clumsy copying, limited metabolism, and unstable compartments. Over time, in a stable enough environment, those systems could diversify and refine their machinery. The resident clock, if it started at all, probably began with a hesitant, irregular tick. On Earth, we read that early history in the shared features of all known life. The genetic code is almost universal. Core metabolic pathways look similar in bacteria, plants, and animals. That suggests a common ancestor, some resident or community of residents, from which everything else descended. But we do not possess that ancestor. It is lost in the geological record. We reconstruct it indirectly, like archaeologists inferring a vanished building from the pattern of its foundations. Elsewhere, if residents ever arose, their histories would be equally layered and hidden. We would not see the first replicators. We would see whatever their descendants had become by the time we looked. That is why our definition has to be rooted in behavior we can recognize across deep differences. We are not trying to count the number of ways life could feel. We are trying to count the number of ways matter can learn to persist, adapt, and remember. So, when we ask whether the universe was capable of hosting residents before galaxies were fully grown, this is what we mean. Not cities staring up at strange skies, not minds thinking about their place in the cosmos. Residents, in the barest, most conservative sense, systems of chemistry that could keep their own patterns going, change over time, and leave behind, somewhere, some trace that they had once turned a house into a home. Whatever those first residents were, they did not arrive empty-handed. Before any pattern could learn to persist, the universe had to assemble a kit of ingredients and tools, scattered through space, waiting for a place to land. If we stay with the image of a house, the moving-in kit is simple and unforgiving. You need a liquid where molecules can move and meet. You need a stock of building blocks that can link into chains and networks. You need sources of energy that do not simply tear everything apart. On Earth, that combination came together as water, organic chemistry, and a restless planet. Water sits at the center of this story for reasons that have nothing to do with taste or symbolism. A solvent, in chemistry, is a liquid that can dissolve other substances. Dissolving is not a metaphor. It means that individual molecules become surrounded by the solvent's molecules. They can drift, bump into one another, and react. In a solid, everything is locked in place. In a gas, molecules move freely but rarely meet in an organized way. A liquid balances those extremes. That is why so much of prebiotic chemistry, the chemistry that takes place before life begins, is imagined as happening in liquids. Water has unusual properties for such a simple molecule. Each molecule is bent, not straight, with an uneven distribution of electric charge. That gives water strong abilities to pull other charged or polar molecules apart and keep them in solution. It can dissolve salts, many organic compounds, and gases like carbon dioxide. It also has a wide temperature range over which it is liquid, at pressures common on planetary surfaces. That range is not infinite, but it is forgiving. A planet can wobble in climate and still keep at least some liquid water somewhere on or beneath its surface. But water alone is not enough. If every molecule dissolved in it were as simple as hydrogen or helium, nothing interesting would happen. The second part of the moving-in kit is organic chemistry. The word organic here does not mean natural or healthy. In chemistry, it means compounds built around chains and rings of carbon atoms, often combined with hydrogen, oxygen, nitrogen, and a few other elements. Carbon is special because it can form 4 strong bonds, arranged in different 3-dimensional patterns. That flexibility allows it to build complex, branching structures. The universe began with almost no carbon. It had to be forged in the hearts of stars and scattered by explosions. Yet, as soon as carbon appeared in sufficient amounts, it began to participate in reactions even before planets formed. Observations of interstellar clouds, the birthplaces of stars, show signatures of organic molecules in their spectra. Spectra are the patterns of light absorbed or emitted by atoms and molecules. By splitting light into its component colors and studying which wavelengths are missing or enhanced, astronomers can infer what substances are present. Those measurements reveal simple organics, such as formaldehyde and methanol, and more complex mixtures on the surfaces of icy grains. When those grains drift into regions where new stars and disks are forming, they bring their chemistry with them. In that sense, the moving-in kit begins to assemble long before anyone could call a world habitable. Space is not empty. It is full of slow, cold laboratories, where radiation, dust, and time build a library of molecules that will later fall into planetary systems. We see evidence of this imported chemistry closer to home as well. Meteorites, especially a class called carbonaceous chondrites, contain a rich assortment of organic compounds. Some of them include amino acids, the small molecules that, on Earth, link into chains to form proteins. Others carry sugars, bases related to those found in RNA, and a variety of other prebiotic molecules. The word prebiotic simply means before life in this context. Chemistry that does not require life but could feed into it. When such meteorites fall to Earth and are quickly collected and analyzed, they show that complex organic chemistry can happen in small, cold bodies like asteroids. No cells are needed. No biology is required. Given a mixture of ice, rock, heat from radioactive decay, and occasional shocks, carbon rearranges itself into a surprising variety of patterns. Comets, icy bodies from the outer solar system, also eject gases and dust rich in organics when they heat up near the sunday. Taken together, these clues tell us that any young planet in a roughly similar environment will be seeded with a rain of complex molecules from the start. Laboratory experiments have reinforced this picture. In the early 1950s, researchers carried out a simple but influential test. They filled a closed flask with gases thought to resemble Earth's early atmosphere, added water, and passed electrical sparks through the mixture to mimic lightning. After a short time, the water turned brownish, and analysis revealed amino acids and other organic molecules. The details of Earth's primitive atmosphere are still debated, and later work has refined the setup. But the broad lesson remains. Under the right conditions, energy acting on simple gases and water will spontaneously produce some of the building blocks of biochemistry. Other experiments have explored different settings. When water circulates through hot rock and then cools, minerals can form thin, structured surfaces. Some of those minerals can selectively bind certain organic molecules more strongly than others, concentrating them and bringing them into close contact. Hydrothermal vents on the ocean floor, where hot, mineral-rich water emerges from the crust, create such environments today. Laboratory simulations show that in vent-like conditions, simple molecules can be driven to form longer chains, including short peptides and nucleic acid fragments. The important point in all of this is not that we know the precise path from simple chemistry to the first residence. We do not. It is that the toolkit appears to be generic. Water, energy, and a handful of common elements are enough to produce diversity, complexity, and sometimes self-organized structures without any guiding hand. The universe does not seem to need an exact copy of Earth to stock a world with ingredients. It needs something like a warm, wet place with access to carbon, nitrogen, and a few metals. Young planets provide that in many forms. A rocky world with active volcanism will outgas carbon dioxide, water vapor, and other gases, forming an atmosphere. As the surface cools, water condenses into oceans, lakes, or seas. Rain falls, rivers form. Minerals weather, releasing ions into solution. Lightning, ultraviolet radiation from the star, and heat from the interior all inject energy into these fluids. On a world with a thinner atmosphere or lower gravity, some water may be lost to space, but while it lasts, it participates in chemistry. Even planets that never form large surface oceans can host water in less obvious ways. Beneath the surface, groundwater can flow through cracks and porous rock. At depth, high pressures keep water liquid at temperatures where it would boil at the surface. This deep water, reacting with rock, can create serpentinization zones, regions where minerals are altered and hydrogen gas is produced. Hydrogen is a potent energy source for many microbial metabolisms on Earth today. Similar environments on early planets or large moons could have provided chemical gradients for prebiotic systems long before any ocean surface stabilized. In icy bodies, as we saw earlier, water can exist as subsurface oceans beneath insulating shells. In such environments, the moving-in kit looks different on the surface but similar underneath. Instead of sunlight driving chemistry, it is tidal heating or radioactive decay. Instead of atmospheric lightning, it is interaction between water and rock at the seafloor. But the essentials remain: a liquid solvent, a supply of simple molecules, and gradients of temperature or composition that can be tapped. There is also the quiet role of time. Prebiotic chemistry does not have a schedule. It explores possibilities slowly, trying vast numbers of combinations in parallel. On a young, unstable world, bursts of activity may be punctuated by catastrophes, impacts, climate swings, eruptions. Some environments will be erased before anything stable emerges. Others will persist for millions of years, allowing cycles to refine. The moving-in kit does not guarantee residence. It just increases the number of tickets in the lottery. On Earth, the record suggests that as soon as surface conditions allowed liquid water to persist, signs of organized chemistry appeared relatively quickly. Carbon-rich sediments, isotopic ratios hinting at biological activity, and microstructures in ancient rocks all point to a biosphere already operating not long after the crust solidified and oceans formed. From the outside, that looks as if the moving-in kit, once delivered, was used with surprising speed. If that pattern is at all general, it changes how we view early planets elsewhere. Whenever a world had water for any significant span, plus an atmosphere and access to organics from both internal processes and external delivery, it was not just a silent rock, it was a chemical engine, running experiment after experiment. Most experiments would never have crossed the line into residency. A few might have approached it, building protocells, autocatalytic networks, or other near misses. Perhaps in rare cases, the right combination of stability and variation appeared, and the resident clock started. The crucial thing is that the moving-in kit does not care about galactic maturity. Water forms early, whenever oxygen and hydrogen are together under the right conditions. Organic molecules appear in interstellar space, in disks, in comets, in asteroids. Energy sources are everywhere. Starlight, radioactive decay, tidal forces, chemical disequilibria. By the time the universe had learned to build the first generation of planets, it had already scattered the boxes and tools of this kit across countless forming systems. So, when we imagine an ancient planet circling a metal-poor star, or a moon with an internal ocean around a young giant, the question is not whether the ingredients were there. They probably were, in some form. The more disturbing question is how many times those ingredients came close to assembling residents. How often chemistry almost moved in, only to be interrupted by events happening far above the scale of molecules and cells. The only place we can watch that interruption not happen, at least once, is under our own feet. Here, the moving-in kit did not just arrive. It unpacked itself, rearranged the furniture, and refused to leave. Earth is not a typical planet in any deep, proven sense. It is simply the one we know in intimate detail. For our question, that is enough. If we want to know how quickly residents can appear once a house is ready, this is the only clock we have. Everything else is models, guesses, and indirect traces in the light of distant stars. So we start with a rough timeline. The best evidence we have says that Earth formed about 4.5 billion years ago from a disk of gas and dust around the young Sunday. At first, it was not a house. It was a glowing sphere of molten rock, bombarded by leftover debris, its surface more like a magma ocean than a crust. Heavy elements like iron sank toward the center, forming a core. Lighter silicates floated upward. Volcanic outgassing began to build an atmosphere of simple gases. There is a name in planetary science for that earliest hellish interval, the Hadean, from the same root as the word Hades, the underworld. It is a label, not a judgment. In this era, the surface was repeatedly reset by huge impacts. Some of those collisions may have been large enough to vaporize oceans and strip parts of the atmosphere. One particularly significant impact, according to leading theories, involved a Mars-sized body colliding with the young Earth and ejecting material that later coalesced into the Moon. Even if the details change, the broad picture is clear. This was not a gentle nursery. The timeline of cooling is hard to reconstruct, but minerals trapped in ancient crystals suggest that solid crust and liquid water existed surprisingly early. Tiny grains of the mineral zircon, found in much younger rocks, carry ages that reach back more than 4 billion years. A zircon is a very tough, durable crystal that can survive being recycled through geological processes. By measuring the ratios of radioactive elements and their decay products inside such a grain, geologists can estimate when it solidified. Those ancient zircons hint at a world with at least some stable rocks and possibly liquid water on or near the surface while the planet was still very young. Not long after that, in geological terms, the record begins to whisper about residents. The oldest widely discussed signs of life on Earth include two kinds of evidence. One is chemical. Certain rocks show ratios of carbon isotopes that are easier to explain if living organisms were already fractionating or sorting carbon in their metabolisms. An isotope is a version of an element with the same number of protons but a different number of neutrons, making it slightly heavier or lighter. Life, as we know it, tends to prefer the lighter isotope of carbon in its chemistry. When that preference is frozen into rocks, it can act as a faint fingerprint. The other kind of evidence is structural. In ancient sedimentary rocks, geologists have found layered mounds called stromatolites. A stromatolite, in modern environments, is built by mats of microbes. As the microbes grow, they trap grains of sediment, forming thin layers that stack up over time. The result looks a bit like a layered cake made of stone. Some very old stromatolite-like structures might be purely chemical. Others are strongly argued to be biological. Either way, by about 3.5 billion years ago, Earth certainly hosted microbial communities shaping sediments in recognizably biological ways. If those interpretations are right, then the gap between Earth cooling enough to keep long-lived oceans and the appearance of residents was not huge. It may have been a few 100 million years, perhaps less. In human terms, that is beyond comprehension. In cosmic terms, it is quick. The house clock and the resident clock on this world began ticking in close succession. It is important to hold the uncertainty alongside the pattern. Every step in that reconstruction has caveats. Zircons can be reworked. Carbon isotopes can be altered by non-biological processes. Microbial mats can be mimicked by purely chemical layering. The record is broken, partial, and eroded by the very tectonic activity that keeps Earth habitable. We are reading a burned library, not a complete archive. Still, even the most conservative readings leave us with a basic fact. Life has been present on Earth for at least 3.5 billion years, maybe longer, on a planet that is a bit more than 4 billion years old. That proportion matters. It means that residents have occupied this house for most of its existence. Complex animals and plants are late arrivals, showing up only in the last small slice of that history, but the underlying biosphere is ancient. Microbial mats, single-celled organisms, communities of bacteria and archaea trading genes and energy. These have been the main residents for a span of time that makes human history invisible. The only clock idea becomes sharper when we think about how many different catastrophes Earth has experienced without losing its residents entirely. Large impacts did not stop immediately once life began. There were periods of intense bombardment, possible global glaciations, where ice extended to low latitudes, large volcanic outpourings that choked atmospheres with gases. At least once, the planet's oxygen levels changed dramatically as photosynthetic organisms pumped oxygen into the air faster than geological processes could absorb it. Each of these events could have reset the biosphere. None of them did so completely. This shows us something subtle about the resilience of residents once they exist. Life on Earth occupies many niches. Some microbes thrive in boiling hot springs. Others live in ice. Some cling to rocks kilometers underground, in dark, nutrient-poor aquifers. Some drift in the upper atmosphere. When a catastrophe strikes the surface, it may ravage some habitats and hardly touch others. Recovery, in the geological sense, can be rapid, a few million years, sometimes less. To us, that is too slow to witness. To the planet, it is a blink. For our question about timing, that resilience has two sides. On one side, it suggests that once the resident clock has started, it is difficult to stop entirely. Even severe shocks may only prune branches, not uproot the tree. That would be true on other worlds as well, if their residents diversify into multiple niches. On the other side, it reminds us that the earliest, most fragile stages of life's emergence are exactly the ones we cannot see. Before there were robust ecosystems spanning many environments, there must have been a period when residents occupied only a few narrow niches. During that stage, a single catastrophe could have erased all of them without trace. Earth could have experienced such false starts. There may have been prebiotic worlds, earlier than any evidence we now possess, where chemical systems almost became residents and then vanished. If that happened, the geological record does not keep their names. From our perspective now, we can only see the success story that lasted. The clock we read is the one that kept ticking, not any that stopped. Another constraint comes from the way information is shared across Earth's biosphere. All known living organisms on this planet use the same basic genetic code, or near variants of it. The code links sequences of 3 nucleotide bases to specific amino acids. The details of that mapping are almost identical in bacteria, fungi, plants, and animals. That universality strongly hints at a single common ancestor, or at least a single shared genetic framework that became dominant very early. If multiple, independent forms of life emerged on Earth, only one lineage survived to shape the modern biosphere. That again tightens the sense in which Earth gives us a minimum clock. It tells us that, at least once, residents reached a level of organization where they could spread across the entire planet and outcompete or absorb rivals. The time from first replicators to that stage is unknown, but it is not infinite. It is some finite fraction of the billions of years available. That fraction sets the only direct example we have of how long the resident clock might take to move from first hesitant tick to loud, continuous ticking. Astrobiologists sometimes try to turn this into a probability statement. They ask questions like, if life arose quickly on Earth, does that mean it is common in the universe? If we had found that life took almost the entire age of the planet to appear, would that mean it is rare? With only one example, the statistics are slippery. It is like trying to estimate how often coins land on their edge by flipping a single coin once and getting heads. The sample is too small, yet the exercise is still useful as a way to probe our assumptions. One way to frame it is this: rapid emergence on Earth shows that under at least one set of conditions, life does not require almost the entire lifespan of a planet to begin. It can start relatively early. That fact does not tell us how often those conditions occur or how likely the transition is in general, but it removes one simple, comforting story, the one in which life is almost guaranteed to be late everywhere, and therefore unlikely to have had more time than we have. The geological clock also folds into the cosmic clock. Earth formed roughly 9 or so billion years after the Big Bang. By then, the universe had gone through many cycles of star birth and death. Heavy elements were abundant in our region. Galaxies were mature. Many stars much older than the Sun had already burned through their fuel, died, and left remnants. If residents could appear on this planet within a few 100 million years of its surface becoming stable, then there was no physical reason that similar processes could not have unfolded on older worlds, orbiting older stars, in galaxies that were still assembling. This is where the vertigo enters quietly. Earth's history shows a very tight coupling between house and resident clocks. The interval between habitable and inhabited, at least at the microbial level, seems small compared to the available time. If that pattern holds even for a modest fraction of worlds, then the window in which the universe was capable of hosting life opened long before we arrived, and has stayed open for a large part of cosmic history. Of course, Earth's clock also teaches us something about later stages. The leap from microbial life to complex, multicellular organisms took far longer than the leap from planet formation to microbes. For billions of years, the dominant residents were simple cells. Oxygen levels in the atmosphere rose and fell. Continental configurations changed. Climate cycled. Evolution was active the whole time, but the large, visible forms that catch our attention are a late development. This shows that the resident clock is not a single hand moving at a constant rate. It has phases. Early emergence can be fast. Later elaboration can be slow. Intelligence, technology, and self-reflective observers like us may be rare not because residents are rare, but because the path from microbe to mind passes through many bottlenecks. Those bottlenecks may depend on accidents of geology, planetary rotation, magnetic fields, plate tectonics, and sheer contingency. Yet none of those later complexities are required for our main question. We are not asking whether the universe hosted minds before galaxies were mature. We are asking whether it hosted any residents at all. For that, Earth's clock is still enough to unsettle the simple story. It shows a world where life arrives early, persists through violence, and spends most of its time invisible to distant eyes. When we look up from this ground and out into the dark, we carry that knowledge with us. We know that at least one house, in at least one galaxy, did not need the full age of the universe to become inhabited. We know that once residents appeared, they proved hard to erase. And we know that if we had been born much earlier on this same planet, we would still have found a living world under our feet, even if nothing in the sky suggested that houses and residents existed anywhere else. Earth is not a typical clock. It is a single, stubborn tick in an enormous silence, but it is the only one we can read. And when we place it against the timeline of stars, galaxies, and planets, it quietly redraws the boundaries of when the universe could have become capable of life, not as a late, decorative flourish, but as something that might have started moving long before we arrived to notice. Stability, on this scale, is not a gentle promise. It is a temporary truce between many kinds of violence, and in the early universe, that truce was rare. By the time the first decent houses existed, the cosmos had already learned how to destroy them. The same stars that forged heavy elements were also engines of disruption. Massive stars lived fast, burned hot, and ended in explosions that outshone their entire host galaxies for short intervals. Those explosions, supernovae, were not edge cases. In eras of intense star formation, they were common punctuation marks in the story of every young region. A supernova is more than a bright point in the sky. It is a shockwave blasting through surrounding gas, a flash of radiation that can strip atmospheres, and a spray of high-energy particles. Those particles, cosmic rays, are fast-moving atomic nuclei that can tear apart molecules and damage any fragile chemistry in their path. On a nearby planet, a close supernova could alter climate, erode ozone layers, and flood the surface with radiation for years. In the dense, early universe, stars were closer together on average. Galaxies were smaller, their gas more tightly packed. A planetary system in such a region would have more neighboring stars within dangerous distances. That means more chances for a nearby massive star to die violently, more shocks through the local gas, more dramatic changes in the radiation background. Even if a house survived structurally, the environment around it would be repeatedly rewritten. There were other, sharper flashes. Gamma-ray bursts, among the most energetic events we know, are thought to come from particular kinds of stellar death or from collisions of dense stellar remnants. A gamma-ray burst focuses much of its energy into narrow beams. If one of those beams sweeps across a planet, even from very far away, it can deliver a dose of high-energy photons strong enough to destroy upper atmospheres and alter surface chemistry. The early universe, with its population of massive, short-lived stars, may have been more prone to such bursts than the universe we see now. Closer to home, every young star is itself a variable neighbor. Newly formed stars often rotate quickly and host strong magnetic fields. Those fields twist and reconnect, producing flares and outbursts of charged particles. A stellar flare is a sudden release of energy on the star's surface, sending out streams of high-energy radiation and particle winds. On a planet with a thin atmosphere or weak magnetic shield, such flares can strip gases away, erode protective layers, and shower the surface with radiation that breaks apart complex molecules faster than they can form. Many of the smallest, coolest stars in the universe, the red dwarfs, are particularly active in their youth. They flare often and powerfully compared to their quiet, mature phases. Because their habitable zones sit close in, any planet with liquid water would orbit near the star, where flares hit harder and tidal forces are stronger. Tidal forces are differences in gravitational pull from one side of a body to the other. They can lock a planet into keeping the same face toward its star, creating permanent day on one hemisphere and permanent night on the other. That kind of locking is not fatal to habitability in principle, but it complicates climate and makes a planet's atmosphere more vulnerable to direct stripping. All of these effects are moderated, on some worlds, by magnetic fields and atmospheres. A strong magnetic field can deflect charged particles. A thick atmosphere can absorb high-energy photons and re-radiate their energy as heat. Earth enjoys both protections. Its magnetic field, generated by motions in its liquid iron core, carves out a bubble in the solar wind, diverting many particles around the planet. Its atmosphere filters ultraviolet light that would otherwise break apart essential molecules at the surface. Without these, Earth's surface chemistry and its residents would face a harsher sky. In the early universe, strong planetary magnetic fields may have been less common. Not because physics was different, but because many planets orbited closer to more active stars. Close orbits mean stronger tidal interactions. Over time, those interactions can slow a planet's rotation. A slowly rotating planet may have a weaker magnetic dynamo in its core, and therefore a weaker magnetic field. A world with little shielding, sitting close to a flaring star in a busy star-forming region, occupies a very unforgiving neighborhood. Even where the radiation environment was not extreme, gravitational dangers waited. Young planetary systems are dynamically unstable. Their planets migrate, scatter, and sometimes collide. Smaller bodies rain down onto larger ones. This is what planetary scientists call a heavy bombardment, a period when impacts from asteroids and comets are much more frequent than in later, quieter eras. Large impacts can vaporize oceans, melt crust, and throw atmospheres into space. They can also deliver water and organics. As we saw earlier, they act both as builders and as demolishers. On Earth, the late stages of bombardment seem to have eased around the time life appears in the geological record. There may have been survivable refuges even during the worst phases. Deep sea environments, underground aquifers, subsurface ice. But in a typical early planetary system, especially one in a crowded region of a young galaxy, the heavy bombardment could have lasted longer or been more severe. A world that almost stabilized might be reset again and again before residents had a chance to spread beyond the most vulnerable niches. Beyond the local systems, galaxies themselves were rough places in their youth. Many hosted actively feeding central black holes, the engines behind quasars and active galactic nuclei. A quasar is a galaxy whose central black hole is accreting gas at a high rate, converting gravitational energy into powerful radiation across a wide range of wavelengths. Near such a center, radiation fields are intense, gas is turbulent, and stars move in crowded orbits. Any planetary system there would face hazards far greater than those in the quiet suburbs of a modern spiral galaxy. Gas flows within young galaxies added another layer of instability. Streams of material fell onto galactic disks. Mergers between small proto-galaxies were frequent. When galaxies collide, their stars largely pass by one another, but their gas clouds smash together, triggering bursts of star formation. That means yet another generation of massive stars and supernovae lighting up the scene. For houses unlucky enough to sit in such merging regions, the neighborhood could be transformed on timescales shorter than the time it takes for residents to adapt. Put together, this paints a picture that is the inverse of the comforting one. The raw ingredients for life may have been available early. Houses may have been built early. Residents, at least in simple forms, may even have appeared early where conditions briefly aligned. But the background violence, at scales from stellar to galactic, made survival much more difficult. The question shifts from, could life begin, to, could it endure? There are traces of this tension, even in Earth's own past. Some studies have suggested that large impact events or radiation bursts might have pruned early lineages, shaping the tree of life by periodic culling. Others have proposed that temporary global freezes could have pushed life into refuges, favoring certain metabolic strategies over others. Whether or not these specific scenarios hold, the broader idea is straightforward. External shocks do not just threaten life, they guide its evolution when it can survive at all. In the early universe, the shocks were stronger and more frequent. For residents just barely across the threshold from chemistry, with limited complexity and little redundancy, that difference could be fatal. A planet might host prebiotic chemistry for millions of years, perhaps even simple residents, only to lose them to a nearby supernova, a prolonged flare phase of its star, or a late giant impact. From the outside, looking billions of years later, such a world would show no clear sign that life had ever been there. That is the quiet possibility sitting in the phrase violent neighborhood. The absence of lasting residents does not necessarily mean the absence of beginnings. It may mean that the universe ran many early experiments that never had a chance to mature. Houses were built on floodplains and earthquake faults, in the glow of unstable stars, and in the crossfire of colliding galaxies. Some may have hosted residents who moved in, unpacked, and then were swept away before they could leave messages anyone else could read. Seen that way, our own situation becomes less like a first appearance and more like a surviving thread in a much older fabric. Earth formed in a galaxy that had already calmed down from its most frantic youth, at a distance from the galactic center, where radiation is moderate and stellar density is relatively low. The Sun is an unremarkable star in terms of mass and activity. Our heavy bombardment ended early enough that residents had room to spread before the worst external shocks. None of that was guaranteed. All of it shaped the fact that this particular house still holds its residents. For ancient planets that formed closer to the beginning, in tighter, harsher neighborhoods, the odds were different. Their clocks, if they started, may have ticked only briefly before being knocked off the wall. Their stories, if any, are over. From here, we see only the rebuilt houses, the surviving systems, and the long quiet after the early storms. The ruins, if there were any, have been folded into new generations of stars and planets, their chemical traces indistinguishable from all the other dust. Some houses may have been erased so completely that nothing of them remains. Others, if residents ever lived there, might have survived by doing something very simple and very unglamorous. They went underground and stayed quiet. A refuge, in this story, is any place where the violence of the wider environment is muted. Not absent, just reduced. Somewhere radiation is filtered, temperatures change slowly, and chemistry can run in circles for long stretches of time without being reset. On Earth, the most obvious examples of such refuges are not the sunny surfaces we like. They are the places where light barely reaches or never reaches at all. Take a subsurface ocean. The phrase sounds dramatic, but the idea is straightforward. Imagine a world made mostly of rock and ice, far from its star, so cold at the surface that water is frozen solid. If there is enough internal heat from radioactive decay or from being kneaded by tides, some of that ice can melt below the surface while the upper layers stay frozen. What you get is a shell of ice floating on a hidden ocean, with rock beneath that. The thick ice is a shield against radiation and impacts. The water below has space to circulate, dissolve minerals, and carry chemicals from the rock into the liquid. We know such oceans exist in our own system, under the icy shells of several moons. Their names do not matter here. What matters is that the combination of ice, water, and rock seems to be a generic outcome of certain conditions. Tidal heating, the process that warms these interiors, comes from changing gravitational pulls. When a moon travels on an elongated path around a planet, its shape is flexed over and over. That constant flexing produces heat, the way bending a metal wire back and forth warms it in your hand. For an early universe crowded with young, massive planets, such moons would have been common byproducts. Many of those moons would have been cold and inert, but some, in the right orbits, would have had internal oceans that could stay liquid for very long times, even while the surface above was a frozen desert bathed in radiation and stray impacts. If any residents appeared there, they would have lived in darkness, guided by chemistry, not sunlight. Deep oceans on rocky planets offer another kind of refuge. At the bottoms of Earth's oceans, along mid-ocean ridges, hot water rich in dissolved minerals pours out of cracks. These are hydrothermal vents. The name simply means hot water sources. When the hot fluid meets cold seawater, minerals precipitate, building chimney-like structures. Around those chimneys, sharp chemical contrasts exist. Hot versus cold, reduced chemicals versus oxidized ones. Microbes on Earth use those contrasts as energy sources, feeding on chemical differences instead of light. In such settings, life is sheltered from what happens above. A large impact might disturb the surface, even boil away shallow seas, while deep vents go on cycling water through rock. Ultraviolet flashes from a flare or a distant explosion are largely absorbed by the ocean. For a world in a violent neighborhood, deep vent systems could be where residents start, and, later, where some of them retreat, when the surface becomes hostile. Beneath continents and seafloors, another refuge exists: the deep crust. Microbes have been found living in tiny pockets of water within rocks kilometers down, where sunlight is absent and energy comes from slow reactions between water and minerals. On early Earth, and on many rocky planets, water percolates downward through fractures. Radioactive elements in the rock release particles that split water molecules, creating reactive hydrogen and oxidants. This process, sometimes called radiolysis, provides a trickle of chemical energy. It is not abundant, but it is steady, on timescales that make even long cosmic crises look brief. The deep crust does not care about seasons or short-term climate swings. It is insulated from stellar weather and, to a degree, from impacts. A truly catastrophic event can still reach it: a global melting, a complete loss of atmosphere. But many lesser disasters wash over the surface and leave the deep biosphere mostly intact. If the early universe hosted rocky planets with water and radioactive elements, their interiors would have offered similar hidden galleries for residents to persist. Not all refuges are underground. A very thick atmosphere can act as both blanket and armor. On a planet with high surface gravity and abundant volatiles, gases can build up into an air column many times denser than Earth's. High in that atmosphere, harsh radiation and charged particles are absorbed. Deeper down, pressure and temperature can reach levels where liquids form, clouds condense, and chemistry settles into layered structures. In such an environment, the most habitable zone might not be the surface at all, but some floating layer of clouds where temperatures and pressures are mild. On a very hot world, that temperate layer might hang far above a scorching ground. On a colder one, it might sit above a condensed surface ocean. Either way, residents adapted to a particular altitude could, in principle, live in a band of stability even while the layers above and below are hostile. On Earth, microbes and spores are carried high into the atmosphere and survive for surprising lengths of time. They are passengers, not permanent residents, but they show that life can tolerate thin air and strong winds if it is sheltered enough. There is also the possibility of a refuge in motion. Planets that are flung out of their systems by gravitational encounters become wanderers in interstellar space. We tend to picture them as frozen spheres, cut off from starlight, slowly cooling. But if such a planet retains a thick atmosphere, especially one rich in hydrogen, that atmosphere can trap heat from the interior extremely efficiently. Radioactive decay and residual formation heat might keep subsurface oceans liquid for billions of years, with the atmosphere above acting as a lid. In that scenario, a rogue planet could be warm inside while drifting through cold darkness. No sunrises, no sunsets, no familiar cycle of day and night, only a dim red glow from hydrothermal vents under an endless ice roof. To anyone on the surface, if a surface could be reached, the universe would look empty. To any residents in the ocean below, the wider cosmos would be an irrelevant abstraction. Their world would be complete within itself. Even around dead or dying stars, refuges might exist. A white dwarf, the compact core left behind when a sun-like star sheds its outer layers, cools slowly over time. It is small but dense, with a surface gravity far stronger than that of its parent star. Very close to such an object, there is a narrow band where a planet could receive enough light and warmth to have liquid water. That band lies so close that any surviving planet would likely be tidally locked, always showing the same face to its faint sun. But if a planet were to migrate or form there after the violent shedding phase, it could experience long stretches of stable illumination and relatively gentle radiation. From the outside, this would not look like a classic habitable zone. The star would be dim, the orbit tiny, the tidal forces strong. Yet a thick atmosphere, perhaps combined with a small ocean, might smooth out extremes. In the long quiet after the star's main sequence life, such a world could be a refuge that appears late rather than early, a kind of second chance for residents in a system that has already burned through one era. The common thread in all these possibilities is not abundance or comfort. It is shelter and slowness. Refuges are places where time can accumulate. They let weak metabolisms tick over, let small populations persist, let evolution explore, without being erased every time something dramatic happens in the sky. They favor residents that do not need much energy, that can endure long periods of scarcity, that treat change with suspicion rather than enthusiasm. From a detection point of view, that makes them nearly invisible. Subsurface biospheres do not alter starlight passing through an atmosphere in ways that are easy to measure over cosmic distances. Deep crustal communities release gases slowly. Rogue planets and distant icy moons reflect little light. Worlds around faint remnants are hard to find, let alone characterize in detail. If the universe's first long-lived residents made their homes in such places, the odds that we would see them now, with our current instruments, are low. So, when we imagine the early universe, full of young stars and violent events, we do not have to picture it as entirely empty of survivors. It may have been laced with refuges, pockets of darkness under ice, fractures deep in rock, layers within thick alien clouds. In those pockets, chemistry could keep its patterns going while the wider neighborhood raged and then slowly calmed. The first residents with any real chance of continuity may not have looked up at their skies at all. They may have survived by never needing to. If the safest place for a young universe to keep its first residents was under ice and rock, then the question that hangs over everything we have just walked through becomes both simpler and harder at the same time. What if some of them came and went before the sky had even settled into shapes we would recognize as galaxies? When we say before galaxies, we do not mean a universe with literally no structures at all. Even very early on, matter was already gathering into knots and filaments, into clumps that would one day become spirals, clusters, and halos. But those were rough sketches, not the grand designs we see in telescope images. Gas clouds were still falling together. Dark matter was still shaping potential wells. Stars were lighting up in small, lumpy associations more than in smooth, majestic disks. The quiet challenge behind the phrase, "life before galaxies," is this. Do we require a fully grown galaxy for residents to exist, or only a small, local pocket where the right conditions happen to come together for long enough? Everything we have learned in the last century of astronomy points toward the second answer. Gravity works locally. Chemistry works locally. Residents, if they appear at all, do so in very specific corners, oblivious to whether their host galaxy has acquired a neat spiral or remained a clumpy, awkward smear of light. From that perspective, the timeline rearranges itself. Houses can appear as soon as there are stars with disks and a trace of heavy elements. Refuges can appear as soon as there are icy shells, deep oceans, or thick atmospheres. The resident clock can begin ticking in any quiet pocket large enough for a few molecules to stumble into self-copying and persistence. None of those steps demand that the entire galaxy around them be polished or old. They only demand a local truce in the surrounding violence. The fear, for us, lies not in the physics but in the implications. If it is physically possible for residents to have lived before galaxies were mature, then it is also possible that we are not the first wave of life the universe has tried. We may simply be the first one we can see from here, now, with these instruments and this brief window of time. That thought pushes against our instinct to think of ourselves as arriving near the beginning of something, as if the universe had been slowly winding up for our turn. There are at least 3 broad stories that fit what we know, and we do not yet know which, if any, is true. In the first story, the early universe is chemically ready, but dynamically too unstable. Houses form, but they are battered too often and too hard. Prebiotic chemistry runs many trials, but residents are rare and short-lived. Life, in this story, is not truly possible until galaxies calm, star formation slows, and violent events become less frequent. If that is the case, we and our era might still be among the first robust experiments in residents with long-term prospects. In the second story, the universe wastes no time. As soon as there are planets and water and organics, there are residents of some kind. Most of them are simple, microbial, and confined to refuges. They endure in deep oceans, under ice shells, in thick atmospheres, or in the crusts of small, quiet planets orbiting unremarkable stars. Many lineages are erased by local catastrophes or by the slow exhaustion of their habitats. A few manage to persist for spans of time that dwarf the entire history of our species, then vanish without witnesses. In this story, we are late arrivals in a universe that has been sporadically living for a long time. In the third story, both things are true in different places and at different times. Some regions are too wild for residents to survive. Others settle early. Some galaxies host multiple waves of life separated by long, dark intervals. Others produce nothing more complicated than dust and stars. In that patchwork, our planet is neither first nor last, neither central nor peripheral. It is just one house whose residents happen to develop tools good enough to notice that there was a question to ask. The uncomfortable part is that all three stories can fit the same sparse evidence we have. One living world, silence in our detectors so far, and a universe that seems indifferent to our desire for a clear answer. That is why the question feels like something we are afraid to answer. Not because the physics is too strange, but because any honest answer will probably make us smaller than we prefer to feel. If residents did arise before galaxies were mature, where would their traces be now? On planets that have since been stripped of atmospheres, their biosignatures would have been sandblasted away by time. In subsurface oceans around long-cooled worlds, their last descendants might have died in darkness, leaving only altered mineral layers that no one will ever drill to. In rogue planets, wandering between stars, any internal biosphere may have frozen, leaving a fossil ocean sealed forever under unbroken ice. All of that could have happened without leaving a clear mark in the light we catch with our telescopes. There is a quiet asymmetry at work. To prove that life existed somewhere, once, we would need some recognizable signal. A pattern of gases in an atmosphere far from chemical equilibrium. A structure in a rock that is easier to explain as biological than as geological. A repeating spectral feature that matches complex molecules difficult to make without resonance. To suspect that life never existed anywhere before us, we would need something the universe does not offer easily. A complete record of all places and times, checked and confirmed empty. We will never have that. We will always be reasoning inside a shadow. So what can we say? Without overstepping, we can say that the ingredients for life as we know it were present early. We can say that planets, including small rocky ones, formed early, even around stars poor in heavy elements. We can say that refuges capable of shielding delicate chemistry from external violence are not exotic. They are natural consequences of certain planetary and lunar configurations. We can say that on at least one world, life appeared quickly once conditions allowed, and then proved very hard to eradicate completely. Put together, those statements do not prove that there was life before galaxies in the full, majestic sense. They do something quieter. They remove the illusion that there was a long, clear, empty preface to the story of residence. A cosmic waiting room where the universe sat, uninhabited, until galaxies finished their growth and invited life to step on stage. Instead, we are left with a picture of a universe that was biologically capable surprisingly early, whether or not anyone walked through that capability. Maybe that is the part we are really reluctant to face. If the universe did not need to reach our moment of comfort and understanding before it could host residents, then we are no longer at the natural beginning of the story. We are somewhere in the middle of a timeline that started without us and will continue without us. Our existence becomes a local phenomenon in space and in time, nestled among many possibilities that never touched us at all. There is a certain honesty in standing there, in that smaller place. It does not tell us whether the universe is crowded with microbial histories or almost entirely empty of them. It does not tell us if there are or were minds older than galaxies, or if thinking itself is a brief, rare side effect of a chemistry that usually stops at simpler forms. What it does is strip away one layer of unearned certainty. It asks us to live with a universe where we can map the light of the first stars and still not know whether they once shone on residents who are gone. So the question, was there life before galaxies, will probably remain unanswered in the way we usually want answers, with a clean yes or no. a date, an image, a clear discovery headline. Instead, it does something else. It pushes us to widen the timeline in our heads, to let go of the idea that complexity belongs only to the late universe, and to accept that we might already have missed most of whatever living history there has been. If that feels unsettling, that is not a mistake in the science. It is part of what it means to look outward honestly. You do not have to resolve that feeling right now. Let it sit with you the next time you step outside at night, when the sky looks quiet and finished and thin. Somewhere in that darkness, planets are forming, oceans are freezing and thawing, and chemistry is still testing what it can do with time. If you want to keep walking through those questions together, through more of this slow, uncomfortable wonder, you know where to find the next conversation.